In this video, I wanted to do a couple more examples of solving linear inequalities. I'm going to speed it up a little bit, but just because in the last video I talked for quite a while about why, but I want to focus on how and give you guys some more examples to be helpful. So step one is always graphing the boundary line. So if I'm looking at an equation or an inequality such as this one, first I want to pretend, okay, if this were an equation, how would I graph it? And in this case, well, you could rewrite it over here, and this is something, if I was doing it myself, I probably wouldn't even bother, but I have the equation 3x plus 2y is equal to 6. And so we talked about a few different ways of graphing this. One easy way is the intercept method, which is just graphing the zeros. So if I plug in 0 for x, this would give me 2y equals 6, so y would have to be 3. And if I plug in 0 for y, that would give me 3x equals 6, so x would have to be 2 to make sense there. So I could graph this line by finding 2 points. We've got 2, 0 and 0, 3. Or, you could put it in slope-intercept form. However, there's a bunch of different ways that we talked about to graph this, and any one of them is fine. So, we can see this line has a slope of -2/3 and all that stuff. So I could kind of try to continue it to do my best straight line that I can, but it's going to look something like that. And there we go, step one. And step two is to shade in the appropriate region. And notice in my little recommendation, it says if it's solved for y, greater than means shade up, less than means shade down. And so what we could do is we could actually solve this for y, and that would be pretty easy by just subtracting 3x to the other side, which would look like this. And then if I divide it by 2, that would give me y is greater than or equal to -3/2 x plus 3. And so if I solve it for y, or if I put it into function form or slope-intercept form, however you want to call it, we can see that its y is greater than, which again, greater than means shade up in this case. Because if I want to know all the values of y that are above the line, that's exactly what this is saying. We want those y values to be greater than the line, and that's going to result in all of these points. But another really easy way to do it is by checking the origin, because notice that the origin, by using the test point method, I'm going to do it in red as I did in the last video, because some people, I think this is easier or makes more sense to determine which way to shade it. But if we check the origin, what I would get is, well, 0 plus 0 is greater than 6. I don't think so. Notice that does not make sense. And if it doesn't work, then you're not going to shade that region. And the implication is if that point doesn't make sense, we'd have to shade in the opposite region. So that's a another fast, easy way to figure out which way to shade it. But at the end of the day, I have my boundary line, and I know every point above that line is also going to be satisfactory. And if you want to know, well, what's another way that I can check to see if I got this right? Well, you could check all the points on the line and make sure they make sense in the inequality, and you could check all the points over here and make sure they all work as well. But as we can tell, well, there's too many points, right? There's a million points on this line, and there's a million points up here. So it's not really feasible, but that's the point of the methodology, to figure out what parts satisfy the equals part and which parts satisfy the greater than, and kind of put them all together. And one other difference between inequalities like this and the ones we were dealing with in chapter 1 is that if you're wondering how do I write my answer, well, the graph is the answer. Because like back in our linear inequalities, which is one variable, we often wrote our solutions kind of like this, as all numbers from -2 to infinity. But on a single dimensional line, it was very easy to describe that solution using interval notation because there's only one dimension to it. All the values are in a specific region, right? Values where x is greater than -2. The issue with equations such as this is that you can't describe this using a single interval notation because it's not just a single set of numbers. It's not a one-dimensional set. So kind of what I'm trying to get at here is one-dimensional inequalities. You can use interval notation to write, but you can't write this using interval notation because this set of numbers is a lot more complicated. It's actually a set of lots and lots of distinct points, and it's really governed by the inequality to begin with. And if you wanted to know, well, how could I write this using a set notation? Honestly, there is not really a simple way of doing it. They're like interval notation for a two-variable equation, but you can write it using set builder notation if you do this. Basically, if you write the set of points x, y by using set builder notation as we did before, such that 3x plus 2y is greater than or equal to 6. This is a way you could write it using a set notation, which would again be visually represented by all this. But if you notice what I did over here, I didn't really do anything. All I did was I rewrote the inequality in a set. But this is a way that I could write, and so it's kind of silly, and I don't even really want to bother showing you that because it doesn't actually tell me my answers. The value of the graph is I can see, well, what are the answers? What points work and which don't? Again, for a very specific part of the domain and range. So let's do one more. And I wanted to do an example when it was not equal to kind of differentiate between these and before. Because notice that I said if it's greater than or less than without the equals, we want to use a dotted line instead of a solid line. And notice here when I was graphing those boundary lines, I was using a solid line. But in the case of the third example on our packet, if I was to graph the boundary line, that would just be the equation y is equal to 1/2 x plus 1. And this one's pretty easy because it's in slope-intercept yet again. I see that it has a y-intercept of 1 and a slope of 1/2. So if I wanted to graph the points on the line, it would have rise 1, run 2, rise 1, run 2, rise 1, run 2, and so on. I could kind of visualize what's going to happen with that particular linear equation. And actually, technically, when you're graphing points on a boundary line, which is not part of it, you technically want to use open circles as you're graphing it. Kind of like when we were talking about the difference between x is greater than -2 and x is just, or sorry, x is greater than or equal to 2 and just x is greater than -2 separately, right? Because when it's just greater than -2, actually what I have graphed, sorry, is just greater than. So that's why I think I'm confusing myself because my answer was not the same as what I wrote down. I think I was just not thinking as I was writing. But if we put greater than or equal, right, that we write it in a different way. We write it as bracket -2 comma infinity. And when we were to graph the solution on a number line, we put a closed circle on -2. So this is my whole point here, is when you're including your answer, we use a solid dot. When it's not part of the answer, we use an open circle. So technically, I should be using open circles as I'm graphing this, but the reason why most people don't and why it's honestly not a big deal is because, like, especially on a graph as small as this one, it's kind of hard to graph open circles on there. But I'm going to go ahead and do my best try at it. So it's kind of hard to see, but oops, and I even messed those points up because they're supposed to be rise 1, run 2. So this one should be over there, and there, and there, and there. But basically, pretend they're open circles. And when it comes to actually graphing the line, since a solid line represents this equation where y is equal to 1/2 plus 1, notice that this equation does not allow for equality, right? Equality would not be part of this because it's just y is greater than. So the answer is simply the region above it where I shade upwards from the line, but the line is actually not a part of it. And the way we write boundary lines and what are, like, there's a lot of times in math where we use a dotted line instead of a solid line. And in all those cases, they're usually called boundary lines. It's something where your thing is getting very, very close to something but not touching it. And it's conceptually the same as an open circle. It's like I'm getting up until that point, but I'm not including this line as part of my answer. And that's why we have to do it different. Like when we're solving this, we don't graph a solid line just because mathematically that means something different. But I can still see all my answers. My answer is still the shaded region above the dotted line. All of those are part of it up until it. You know, it just helps us to know that difference. In future sections, if we ever do use dotted lines, there's usually a reason why we're going to use a dashed line or dotted. You know, really this is dashed. Dotted is different, but you know what I mean. There's usually a meaning behind doing that. And it's just like the difference between parenthesis -2 to infinity and bracket -2 to infinity. One just means part, one is not. And really, it just is easy, you know, an easy thing to remember is that if your inequality includes equal and you're trying to do this, just use a solid line. If it does not include equality, just use a dotted line. Otherwise, they're exactly the same type of problem.